So hello, welcome. Today we're going to finish chapter 5, which is all basically thermodynamics, although I never actually used that term before. Before I jump in, I sent an email, but I want to put it in, say it now. My office hours, I shrunk today's office hours. I have a meeting from 3 to 4, so instead of 3 to 4:50, they're going to be 4 to 4:50. I assume it's not a huge issue since there was no homework due this week and no lab due this week. But if you wanted to meet with me and planned on being there from 3 to 4, shoot me an email. I will find another time to meet with you. Sorry, I don't always have say on when my meetings happen. But to pick up where we left off, as I had introduced this slide. And I said, this slide tells you how much heat is required to change the temperature or phase of water. And that these series of equations, which I color coded for your convenience, are going to be how much heat is required to do things. And basically what it boils down to is this red equation is how much heat is required to change the temperature of ice. The orange/yellow equation is how much heat is required to melt ice. The green equation is how much heat is required to change the temperature of water. The blue equation is how much heat is required to boil water. And the purple equation is how much heat is required to change the temperature of steam. At any given problem, if I just say, hey, bring water from 20 degrees to water to 40 degrees, which I did an example like that previously, it's nice, simple. I can just use the green equation. But if I give you a problem with a change in phase, you're going to have to figure out which equations you need. And I'm going to go straight into an example of this and try to explain it as I go. Let's say I ask you, how much heat does it take to change 0.2 kilograms of ice at -5 degrees to water at 10 degrees? If I want, see here I have two different phases. I have ice and water. And so if I want to know how much heat it takes to go from ice at -5 to to water at 10 degrees, I need to look at it as 3 steps. See, what's going to happen is my ice at -5 is going to become ice at 0. That's as hot as ice can get. Once my ice is 0 degrees, I will then melt the ice. Once I melt the ice, I then have water at 0 degrees, and I can turn that to water at 10 degrees. How I recommend doing these problems is that color-coded chart I had, this one. I like to go and just put dots right on it and say I'm going from whale to whale. You see, I'm going from sub-0 to 10. That means I'm going from about this black dot to my other black dot. And all of the areas between my dots, that's what equations I need. If I'm going from if I'm going from -5 degrees Celsius to 10 degrees Celsius, that means I'm going to have to use the red equation, the orange equation, and the green equation because I need to go step by step. So I'm going to just kind of make that smaller in the kernel so I can talk about at the same time. And that's what I'm going to say is if I'm going to go from -5 to 10, I have to first go from -5 to 0 for ice. That's my red equation. Then I'll have one equation just to do, and I color coded, just to get to 0 degrees. Because just getting to 0 degrees is its own thing. I have another equation just for melting, and a third equation to get from 0 to 10. I need to split it up in pieces because each phase has its own equation. Now I could go straight to the version with the constants in it. My diagram in the upper right does have the constants in it, so let's go to that version of it. And here is the trickiest part. Here's the part most people get wrong. Is the red and green equation have a t initial and t final. And people like to look at this and say, we start at -5, we go to 10. There's my t initial, there's my t final. T final is 10, t initial is -5. But that's not actually the case. You see, I have to look at each piece individually. Ice is only ice up to 0 degrees. And so what I'll say is my ice will go from 5 degrees to 0 degrees. Because once it hits 0, it's no longer ice. My water My water is going to do the rest of the trip. 0 degrees to 10 degrees. That's going to be my waddle. I don't just put them together and say both of these are -5 to 10. One of them is -5 to 0. The other one is 0 to 10. And this covers the whole spectrum. That I have the heat required to bring ice from -5 to 0. Let's keep the heat required to bring ice from -5 to 0. The heat required to melt the ice, and the heat required that once it becomes water to go from 0 to 10. At this point, I just do all that math and add them up. Any questions though? Okay, so to bring 0.2 kilograms of ice at -5 degrees Celsius to water at 10 degrees Celsius, it takes 77,000 joules. So that's all well and good. But the question becomes, how do we do that? Like, how do we give something 77,000 joules? And so what I want to talk about now is the mechanisms of heat transfer. AKA, how do you add heat to something? How do you heat something up or cool something down? How does heat move? In reality, heat moves in 3 different ways: conduction, convection, and radiation. Conduction is what an electric stove uses. Heat by conduction is you take a hot thing, you take a cold thing, and you push them against each other. See, what happens if you have a hot thing is it has really fast moving molecules. We have a cold thing that has slow moving molecules. And if you put them together, the fast moving molecules are just going to keep hitting the slow moving molecules till everyone's moving at a different speed. That is what conduction is. It is the heat by something touching something else. You jump into cold water and you feel colder, that's conduction. It's just the fast moving molecules hitting the slow moving molecules, slowing them down. Once again, an electric stove is conduction. Now, conduction will occur anytime there's a difference in temperature between the two things. If you have something at 20 degrees and something else at 20 degrees and put them together, all the molecules are moving at the same speed. Nothing's going to happen. But if you take ice and put it in a drink and the ice melts and the drink cools down, that's conduction. They're physically touching. I just knocked down my post-it note. Now, how fast something conducts is based off the thermal conductivity. And so things that conduct well, like metals, have high thermal conductivity. That means they can transfer temperature well. And things that can't transfer temperature, like styrofoam or cotton or ceramic, have low thermal conductivities, where I gave some thermal conductivities to the right. Things that conduct well, we call conductors. Things that don't conduct well, we call insulators. This is the basis of almost everything you do to keep your house warm. Like insulation in the walls, that's just something with a low thermal conductivity to reduce heat loss of the hot air inside your house touching the cold air outside your house. Multi-pane windows, it's just to fill it with a gas with a low value of thermal conductivity to reduce heat loss of, once again, the hot air in your house that's touching the cold air outside your house. That is conduction. Now, let's say you want to heat an area the oldest way possible, and make a fire. Say you got a gas stove. So you got a gas stove, and the flames are coming up, right? The flames might not be touching the pan, but the actual things that are hot are not touching the pan. It's just the fire is beneath it. It gets hot. The second mechanism of heat transfer is convection. And convection is energy transfer by the movement of a substance. Convection is basically heating something by blowing hot air over it. See, if you make a fire, when you make a fire, it's going to heat up the air right at where the fire is. When you heat up the air right at the fire is, thermal expansion, the air is going to expand. As the air expands, its density is going to change. As its density changes, the hot air is going to rise. And so the area right above a fire is really hot because it has hot air coming past it. That anytime you blow, like a hair dryer is convection, blowing hot air on something. Forced air in a house where you blow hot air through the house. That's convection. Convection is changing the temperature by blowing hot air on it or some other substance. Water cooling is cooling by convection. It's by shooting cold water at it. That's just not staying. And so convection is change of heat by blowing air at it for the most part. Now, this is why if you put your hands directly over a fire, it's hot. It's because the hot air is passing your hands. But you don't have to be above a fire to feel heat. If you stand next to a fire, it's still hot. And so that's something slightly different. The third way to transfer heat is called radiation. And here's the general idea. All things at all times radiate electromagnetic waves. This is because the molecule is moving. And as we said earlier, how fast the molecule is moving, that's based off temperature. The faster the molecules move, that's going to change the spectrum of electromagnetic spectrum they put out. And what happens is, everything absorbs radiation. And the hotter something is, the more radiation it puts out. It also shifts closer to blue. So things at room temperature put out infrared light, which we can't see. As it gets hotter, it'll eventually glow red, like red hot. If it gets hotter, it'll glow blue. That's just electromagnetic radiation. And if you make something hot enough, it will radiate electric light. It will radiate electromagnetic spectrum. It will radiate light. And that light can be used to heat things. This is how the sun heats the planet. The sun is super hot, so it radiates electromagnetic rays. Those electromagnetic rays travel through space with no physical contact. It can't be conduction because the sun isn't touching the earth. That would be bad. There's no convection because there's no gas that's flowing from the sun to the earth. That would just be weird. But it's just that the electromagnetic rays can travel through space. Now, in general, dark things absorb radiation, light things reflect radiation. That's why if we wear a black shirt in the summer, it gets real hot, or like the asphalt in the summer, because it absorbs radiation and heats up. Any questions here so far? Now, if you want to keep something and have it not change temperature, you need to think about all three of these. A good thermos, which this is an okay one. I need to have someone cut one in half for me, but I'm always know that I'm just going to end up cutting myself once I do, so I never bother. A good thermos is made in such a way to minimize all three of these. What they normally have is double walls. That this has that kind of hollow noise, even though it's filled with water right now. Is what it is there's a cup inside a cup with a vacuum, or at least a partial vacuum in between. By going and putting a cup within a cup with an area between, that'll reduce heat loss by conduction because there's nothing physically touching, in this region right here. They also, you keep it closed. If you keep it closed, no air is going to blow in. No air blows in, there's no convection. And you'll find that most thermoses are silverly, like not made of silver, but like silvered, like metallic looking. The reason why is radiation is electromagnetic rays. Electromagnetic rays are light. And what happens when light hits something shiny? It bounces off. See, most thermoses are made with a surface that is silvered so that it bounces all radiation. And therefore, it cannot lose heat that way. And yeah, that's how you keep heat loss and things. Okay. Any questions there? I'm going to kind of jump topics next. So I want to make sure there's no questions before I completely jump topics. Okay. And now for something completely different. Oops. Phase of the metal. You're probably familiar with the phase of the metal. Solid, liquid, gas. You might know plasma. We'll talk about them a little bit. And we now know how much heat is required to change the phase of something. Here's the idea. Solids. Set shape, set volume. That this guy has this volume, he always has this volume, his shape doesn't change, it's pretty set. The reason solids have a set shape and set volume is that the atoms or molecules, whatever it is, are held in a rigid structure. That they're all stuck in a right spots from each other. Except, once again, temperature is speed of molecules. They might be stuck in nice rigid things, but they'll be vibrating back and forth. Kind of like the pictures in the bottom right, or GIF in the bottom right of the screen. That my GIF in the leftmost on the bottom right makes sense. So it's 5 degrees. And what you can see is that all these molecules are kind of bouncing around. But the thing is, they can't move relative to each other. They can bounce around, but they're still kind of like, uh, this one is always to the left of that one. Oh, that is not a color that showed up well, though. This one is always to the left of that one. They're always kind of in the same relative position. When you increase the temperature of a solid, we've already said that things get bigger, that as you increase temperature, things grow. The reason they grow is that at higher temperatures, the vibrations get bigger. And that you can look when I go from 5 degrees to 40 degrees Celsius on these scales, that the 40 degrees have a lot more movement. That a lot more movement is what makes the object bigger. And we'll go and they'll just be stretching around. It's still a rigid structure. My one dot here is still always to the left of my other dot there, but they're just bouncing around a lot more. That's why things get bigger at bigger temperatures. The thing is, if you keep adding heat, eventually they'll vibrate so rapidly that all of these bonds inside, all those little black lines, will break. This is why adding heat can melt something. That if you add enough heat to melt something, you are literally just breaking those bonds, and they go from vibrating around to vibrating freely. A liquid has a set volume, but not a set shape. That liquids will match whatever shape they're in. The reason why is that there is still some semblance of bonds between the molecules, that there is something keeping them from moving away or apart from each other for the most part, but they're no longer constrained to be just to the left or right of each other. They can now move around each other at will, causing the lack of shape. That enough heat broke the vibrations of the solid. And what will happen is in a liquid, all the molecules will be vibrating around. And they'll just be going, but as I said, they can't really get closer to each other or further away from each other. They will change volume slightly with temperature, just like the solid change volume slightly with temperature, but it won't be much. Now, if you keep heating it up, what's going to happen is these molecules are kind of whizzing around each other. If you keep heating them up, they're going to go faster and faster and faster and faster. And eventually they'll be going so fast, some will just pew and break free and get loose. That's boiling. A gas has no set shape or set volume. There is no force holding the molecules together. They do whatever the hell they want. In general, when I put air in this, I can change the shape of this will match whatever the shape is. And the volume will match temperature or how much I squeeze it. That you can take a gas and compress it, like putting air in a tires, that you're compressing more air in. The volume is not set, because that they're all broken free. They're moving so fast that they can't be constrained. Now, if you keep heating up, you can eventually become a plasma. A plasma is when you heat up the atoms so much they move so quickly they rip themselves apart. We're not really going to talk about plasmas. Just know that's what it is. Moving so fast, they destroy themselves. Now, any questions there? Okay. For the rest of the day, we're only going to talk about gases. Because gases, because the volume can change, have some really weird effects. And for the record, if we want to talk about every gas in general, it would be complicated. We're only going to talk about what is called an ideal gas. An ideal gas is something that always behaves the way we want it to. Real gases, like ones that really exist, normally look really close to ideal. That most gases you can assume is an ideal gas. Unless you get to very low temperatures, aka they're almost a liquid, or very high pressures, like we are creating diamonds high pressures. But as long as you're not near those extremes, we can treat any gas as an ideal gas. And in an ideal gas, there is something called the kinetic theory of gases. This just describes how ideal gases work. And here's the general idea. All matter is made up of very small molecules, including gases. In a gas, though, the distance between molecules is large. That if you have a region of gas, that there's a good amount of molecules in this balloon, but they are smaller than the space between them. There's mostly a vacuum in here, including the air around me. It's mostly vacuum, with very, very small molecules decently far apart. There's enough gas that I can breathe, but they are very spread out. That gas molecules themselves occupy a negligible amount of volume in a gas. And what happens is all the molecules in the gas move rapidly in straight lines until they hit something. That this is filled with a whole bunch of molecules just whizzing around in every direction. And what will happen is they'll just move in a straight line till they hit a wall. And once they hit a wall, they move in a straight line till they hit another wall. Then they'll move in a straight line till they hit another wall. Then they'll move in a straight line till they hit another wall. Then a straight line till they hit another wall, and so on. Ping-ponging across the sides. I'm trying to use my video screen as my thing. I'm ping-ponging around, but having a hard time. Now, in an ideal gas, there is no attractive force between molecules. That all molecules are, one molecule doesn't get pulled towards the other one. And most of the time, the molecules will not collide because there's no, they're so small and they're so spread out. And so what it is, the molecules are really small, so they never collide with each other, and there's no attraction between them, so that they don't get pulled towards each other. When a molecule hits the wall, it'll just bounce back off in a straight line. Now, sometimes they will collide with each other. Whenever they do collide, it's what is called an elastic collision. Energy is conserved. They don't gain or lose energy. Sometimes one moving slightly faster might hit one moving slightly slower, but all that's going to happen is the second one will speed up, the first one will slow down. It will follow conservation of momentum. But for the most part, that doesn't happen. It's mostly them just bouncing off the walls. Now, if you have a chamber of gas, they'll just go boop, hit the wall, and go off. And then another one will go boop, and hit the wall, and go off. But let's look what happens with my hand when I do this. If I have something go and hit my hand and come off, it bounces my hand back. Newton's third law, that if I hit my hand with my other hand, there's a force backwards. And that if I keep just pounding on the walls, they get pushed out. That is called pressure. When you put gas inside something, the molecules are whizzing around, and every time they hit the wall of the chamber they're in, they ram into it and bounce off. And every time they ram into it and bounce off, they push on the walls a little bit. You can feel exactly how much they push off the walls. Pressure, which uses the symbol P, is defined as force over area. It's how much force they apply when they hit the wall over the area they go in. For the record, the units for pressure is pascals, capital P, lowercase a. Same thing as a Newton per meter squared, where the American unit is PSI, pounds per square inch. And so when I put air in this balloon, the reason when I put air in this balloon that it holds this shape, that it has this set shape being as far as it wants, it's because all the molecules are just ramming into the walls of the balloon over and over again, pushing on it and pushing it apart, giving it the shape. That's what pressure is. It's the molecules bouncing off the walls. Okay? Now, if you want to mess with the pressure of gas, there's a lot of ways to do it. And I'm going to kind of go through most of those. The easiest way to mess with the pressure of a gas is change how much air is in there. That if I put only a little bit of air in this, there's very little pressure. I can kind of mess with it easily. If I put more air in it, it has a lot more pressure inside here. That by increasing the number of molecules, which I'm going to use the symbol capital N for number of molecules, I increase the pressure. Quick thing, real fast. I'm using a symbol here that not all of you might be familiar with. Right there, that symbol. That means it's proportional to. That means if I double the number of molecules, it doubles the pressure. If I cut the number of molecules in half, it cuts the pressure in half. That just means is proportional to. It goes as a 1-to-1 ratio. Now, the reason for this is, think about it this way. Pressure is the molecules hitting the walls. If you're in an empty room and you're just going to walk in line so you hit the walls, you're not going to hit it very often. If you jump into a big fucking mosh pit, because that's a thing that used to exist in the before times, you're going to be hitting people continuously. Hitting more walls, hitting more things, that means more pressure. That's why. The more things in a chamber, the more often pieces are going to run into each other. And that's why increasing N increases the pressure. Kind of an interesting thing with this. When I inflate this balloon, I'm increasing N. Because I'm increasing N, I'm increasing P. What I did is I made sure the pressure inside this balloon is not the same as the pressure outside of it. And if I let go of the balloon, it gets squeezed and the air goes flying out. That's because the pressure in the room squeezes the balloon shut. If you take a balloon, and let me make this a little smaller. If you take a balloon, inflate it, and you can see when I let go, it just goes away, and remove the exterior pressure, inflate, remove the pressure from the air by putting a cork in it, it'll stay inflated. The reason that balloon that's now on my cat scratching post deflated is because air around. There's air pressure. There's a pressure pushing down on you right here. Squeeze the air out. And that if I remove that air pressure, there's nothing going to squeeze it out. The pressure in the balloon can just stay as what it was. Okay? Now, other ways to mess with pressure. What is temperature? Anytime, okay, pressure is how hard things hit the walls. And temperature is related to how fast molecules are moving. So let's say my arm is the wall of my balloon here, and it's cold. The molecules are going to go, and kind of bounce off. And then if you heat it up, they're going to go, and bounce off. The hotter the temperature, the faster the molecules move. That actually punched my hand hard enough to hurt. Actually, I caught my ring, that's why. And so if something's really hot, it's going to hit the walls harder. If it hits the walls harder, that's going to be more pressure. So anytime you increase temperature, the pressure goes up. Likewise, it's a 1-to-1 ratio again. Likewise, if you decrease the temperature, your pressure goes down. If you are fancy enough to have a car that tells you when you need to put air in your tires, you'll know that the first cold day every year, it tells you need more air in your tires. The reason why is because if the temperature of the room goes down, or the temperature outside goes down, the pressure goes down because the molecules hit not as fast. Now, for the record, for this equation, or it's not really an equation, this is an equality, but we're going to have to work in Kelvin. So if you go from 10 degrees Celsius to 20 degrees Celsius, that is not doubling the temperature because we're working Kelvin. That's only 283 to 293. But if you double the temperature in Kelvin, you double the pressure. To show this, what I have here is a can that was mostly just filled with air. There was a little bit of water in the bottom. And I heated it up to 500 degrees. You know what? I'm going to turn on audio today. I heat up to 500 degrees. And so what is right now is that inside this can is the water vapor because it was mostly empty, which is really, 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 really hot. And it's open on the top. Because it's open on the top, that means the pressure inside the can equals the pressure outside the can because it's open to the air. I'm going to invert the can into the ice water. By inverting the can into the ice water, I'm going to seal the top because it's stuck on the water, and it's going to decrease the temperature. If I use my mouse, if I decrease the temperature, I decrease the pressure. Like how I turn the sound on. And that by decreasing the temperature, I caused the can to crush itself. It crushes itself because it had a lower pressure. It made a vacuum. Oh, that's why. My headphones were super quiet. Any questions though? To show you a more impressive version of this, which I should turn off the animation though. Animations. I'm just gonna do it real fast before I forget. To show you a more impressive version of this, you got this guy. This is a thing filled with hot air. It's out in the cold, so it gets colder. It'll crush itself. All that is a decrease in temperature causing a decrease in pressure. Okay. Now you can also affect pressure with volume. So once again, what pressure is how hard, how often things hit the walls. So I'm going to use my screen, my video camera again. Let's say I got an air molecule just bouncing from one side to the next at a nice set speed, saying the same temperature. It's going to hit every so often. If I put a wall halfway, it's going to hit walls more often. And if I make it smaller, it's eventually going to be like ding, 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 off the side. That's because if there's less space to move, you're going to hit things more often. Once again, if you're running around outside, you're probably not going to hit a wall very often. If you're running around crazy inside, you're going to hit walls more often. Therefore, pressure and volume are inversely proportional. Anytime you double the volume, your pressure cuts in half. If you cut your volume in half, your pressure doubles. To show this, what I have here, nope, not that one. We'll come back to that video. What I have here is two balloons and a vacuum chamber. What I'm going to do is I'm going to suck the air out of this chamber. By sucking the air out of this chamber, I am removing the pressure. I'm decreasing the pressure. When I decrease the pressure, these balloons are sealed, they're closed off. But as I decrease the pressure, what's going to happen is the volume is going to increase. And you can see that the two balloons are getting a little bigger. Give them a little more time. That's just because if I am decreasing the pressure. If I decrease the pressure, it must increase the volume. And there you go. If I bring the pressure back to air pressure by opening the valve on the bottom. Screw, screw, screw. Come on. Takes a second for me to open it. They go back to the volume they had when I return the pressure to what it was. Okay. Now, this says that we can change the pressure of a gas by changing the number of molecules, the temperature, or the volume. It's of note, though, the other ones are related also, like volume is proportional to temperature, that if you double the temperature, you might not just double the pressure, you might double the volume instead. That changing the temperature of something can affect the volume. It's kind of just to throw that in there. In this video, what I have is 4 balloon animals and some liquid nitrogen. Liquid nitrogen is 77 Kelvin. It's very, very cold. And what's going to happen, and I don't know how loud this is going to be, so that'll be fun to find out. What's going to happen is we're going to take these room temperature balloons and decrease their temperature from about 300 Kelvin to 77 Kelvin. That shouldn't be too loud. But then again, it's not too loud for me. I'm always for you guys. By decreasing the temperature, we would decrease the volume. And that these balloons will basically deflate. They're still holding the air, it's just having a very, very, very small volume inside of them. When the temperature goes back up, the volume will go back up. And so these will go back to full size once the temperature goes up. Because, yeah, just going with these laws. Okay? Now, all these relationships, I went through a lot of relationships, but here's the thing. We're going to turn them into one law. Instead of doing all these individually, you're just going to say one equation to take care of all of it. And this is called the ideal gas law. With the ideal gas law is, let's take all of these, the relationship of pressure, temperature, number of molecules, volume, and link them in one spot. It is the gas law. It is the gas law to explain all gases, or at least all ideal gases. And it is as follows. PV equals N K sub BT. This equation, all those things I had, all those proportionalities, that if you up P, V goes down. If you up N, P goes up. If you up T, P goes up. All those boil down to this. In this law, P stands for pressure, which will always be measured in pascals. If you're in a different unit, convert it. V will always stand for volume, which is going to be measured in meters cubed. If it's in something else, convert it. N will be the number of atoms of a gas. Literally, count how many atoms you got. K sub B is a constant. K sub B is called Boltzmann's constant and is and always will be 1.38 times 10 to the negative 23rd joule per Kelvin. And T is the temperature, but it must be in Kelvin. Most of the time you're given temperatures in Celsius, but you're going to always have to convert to Kelvin for this equation. Now, for some of you, you might have said, I've learned the ideal gas law before and it wasn't that. Some of you might know PIV, PV equals nRT. This is one of the weirder things. Chemists have their own version of the same equation. Chemists like to work in ATM for pressure, liters for volume, and for number of molecules, they instead use moles. Well, moles is the dumbest fucking thing ever, and I don't know why chemists use it. In fact, we'll teach it later on, and I'll mock it then too. Why? It's like saying you have 3 dozen of something. Just say you got 36 of it. Why say 3 dozen? If you're used to PV equals nRT, I would recommend not using it in this class and using the one I introduced. The reason why is because I'm going to be giving you values to match it. Once again, pressure will be in pascals. That should be a capital P. Volume will be in meters cubed. N is number of atoms. K sub B is 1.38 times 10 to the negative 10. Sorry, 1.38 times 10 to the negative 23rd joules per Kelvin. And T is just the temperature in Kelvin. Okay. I'm going to show one more video before I do an example problem. This video is near and dear to my heart because the process of filming it, A, gave me a skull, and B, almost got me arrested. So fun memories. General idea is most of the shots in this video are us doing practice runs for an open house. And the last piece of the video was during the open house. And here is what we did. We took a soda bottle and put a little bit of liquid nitrogen in it. Not much. You can see the fill line. Liquid nitrogen, as I said before, is at 77 Kelvin. We then sealed it real tight and put a plastic garbage bucket over it. Side note, not a mop bucket. Those explode. That's what the skull is from. You can actually see the mop bucket when I start the video. What happens is this liquid nitrogen becomes gaseous nitrogen at 77 Kelvin. It boils. And it fills that plastic bottle with 77 Kelvin gas. Because that gas is in the air, which is about 300 Kelvin, it slowly heats up. And as it slowly heats up, the bottle is contained. So it can't change volume. It can't change volume because it's a sealed bottle. So it changes pressure. And what happens is the pressure will slowly get more and more and more as the temperature gets higher and higher and higher. There's only so much pressure the bottle can take, though, and eventually the bottle explodes, which, according to one professor, sounds like a gun blast. That's how we got the cops called on us. And what happens when this explodes? It fills the bucket with nitrogen gas. Once it fills the bucket with nitrogen gas, the pressure would go down a little bit because the volume went up, but it's still a lot of pressure, and enough pressure to make the bucket shoot upwards. Now, the last bit of this video, you're going to see some people watching it happen. Those people are on the second story in the stairwell. Also, fun fact, it takes about 15 minutes to explode after you seal the bottle, which is just enough time to no longer be paying enough attention to it, to the thing that's going to explode behind you. Yeah, there's the mop bucket. The video isn't 15 minutes long, don't worry, but just a fun fact about it. Light at the top and know if anything went in. Like, well, we're not going to go up 5 stories. And like, figure how I went. Boom! Hits the window. Like, that's how you do it. Wow. Holy mackerel. Oh, worked! Okay, yeah, you can. Got it. All that is the ideal gas law in action. Okay. Okay, 9 minutes left. I'm going to do an example problem. So here's my example problem. A pressure cooker works by greatly increasing the pressure inside, affecting cooking times. A sealed pressure cooker has a volume of about 5.68 times 10 to the negative third meters cubed. I worked that out in, literally I found one on Amazon and looked how big it was. If water is closed at room temperature and atmospheric pressure, how many air molecules are in the cooker? And I'll come back to B. What I'm saying is that it has a pressure of 1.01 times 10 to the 5th pascals. I'm saying initial because part B changes the pressure. We'll come back to that. And I said the volume is 5.68 times 10 to the negative third meters cubed. And I said the temperature was 20 degrees Celsius. Now, in ideal gas law, you always need to work in Kelvin. If you're not working in Kelvin, it's not going to work out. And so I have to convert Celsius to Kelvin. I do that by adding 293. And what I know is the pressure of a gas times the volume of a gas is nKT, where K is that constant. See, I can use this to find how many air molecules are in that pressure cooker. I'll simply divide both sides by KT. If I divide both sides by KT, I get N alone. That the number of molecules is PV over KT, which will allow me to plug in my numbers and solve. Note, N should always be a big number. If you get some small number for N, you probably messed up somewhere. 10 to the 23rd, pretty big number. Okay, let's say someone's actually using this pressure cooker though. They seal it and turn it on. See, that pressure cooker, which once again, I just found on Amazon Reddit stats, it's good up to a temperature of 121 degrees Celsius. If this thing hits 121 degrees Celsius, what's the pressure become? Well, what I'm saying is for now 121 degrees Celsius, that's 394 Kelvin. Because once again, I just add 273 to convert. And I'll use my same ideal gas law. I'll say if I want to know the pressure, there's my law. I'll simply divide both sides by V. And I can say the pressure is going to be the number of molecules, which if it's sealed, that's not going to change, right? If I put so much air in it and then close it, the number of air in it's not changing. Case of B, not going to change. It's not going to change because it never changes. Although I wrote case of B in a weird unit there. It's the same as a joule per Kelvin. I don't know why I put it in that form though. The temperature is now 394 and the volume was a metal pan. Its volume isn't going to change. The only thing that changes is the temperature. And I can go and I can solve for the new pressure. And I can find that it went from 1.01 times 10 to the 5th pascals to 1.35 times 10 to the 5th pascals. Questions? That is actually the end of this chapter. 5 minutes early. No homework due tonight. Tonight being the 10th. There's no homework due tonight, but You are now good to do the homework due the 17th. I've covered everything. It's probably not a bad idea to start it. No lab due Friday the 12th, but the lab will open Friday the 12th, so it might not be a bad idea to start it after Friday. Once again, I'm took an hour off my office hours today, but unless there's questions, that's it. So, have a good day.